Welcome back, scholars. This is Remote Learning Week 5. Today's lesson is about chemical equilibrium. Before we start, we will do our mindful minute. So make sure you're sitting with a mindful body with your head, neck, and spine aligned. And we'll take deep breaths together. I invite you to close your eyes or you can watch the animation on your screen. And together we will inhale through our nose, nice deep breath, and exhale. Inhale, fill up your lungs, and exhale. Inhale, nice deep breath, and exhale. Inhale, energizing oxygen. Exhale, carbon dioxide. We're halfway there. Nice deep breath in, and exhale. Inhaling, energizing oxygen, and exhaling. And last one, nice deep breath in, and let it go, exhale. Allow your breathing to return to normal. And when you're ready, you can slowly open your eyes. Okay, so welcome back. Some things that I do want to point out to you guys, some announcements. For this week, we are publishing all of the lessons and assignments in just 2 parts. So that's why you'll notice for today, there's only a part 1, but it has both the lesson and the assignment. And this is at the request for admin so that we can simplify the number of submissions that students are making and number of notifications that they're getting. And so that if you miss an assignment, it simplifies the number. So if you don't hand in part 1, it's going to say that you're missing 1 assignment, as opposed to before, it would say that you're missing 2 assignments. So you'll get part 1 today, and then you'll get part 2 on Wednesday morning. I'm also going to attach a survey to today's work to see if you guys are liking having your assignments posted on Mondays and Wednesdays instead of all on Monday. Again, that was a request from admin that we try to do that instead, just to lighten the load for you guys and help you spread things out. So you can let me know in the survey if that's working out for you, and if not, I can go back to posting everything on Monday. So today's lesson is about chemical equilibrium. And I know you've heard this term equilibrium before. So I want you to recall, what do you know about equilibrium and what does it mean to you? And today's learning target is I can predict how factors shift equilibrium. Pause the video now so you can write down the learning target. Okay, so we're going to watch a TED Ed video called What is Chemical Equilibrium? And there are check for understanding questions that go with this. So as we watch, I want you guys to keep in mind, what does chemical equilibrium mean?
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now, the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually, they'll meet. They'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Okay, so hopefully you have some ideas now about what chemical equilibrium means. And in this video, there was a mention of collisions. So chemical reactions actually happen and can be explained by something called collision theory. So collision theory states that a chemical reaction is most likely to occur if reactant particles, one, collide with proper energy, and two, collide with proper orientation or alignment. So we're going to look at a GIF or GIF, whatever you call it, of collision theory. And as we watch, I want you guys to notice what happens over time. So begin watching. What do we notice happens over time? And end. Let's watch it one more time. Okay, so what did you notice? You should have noticed that after a few seconds, these red molecules start to appear. So that would indicate that at some point there is a collision that creates the red molecule. So two of the reactants come together to create something new. So those reactants must have collided with the proper energy and the proper orientation or alignment towards each other. Here's a zoom in of those two pictures. An unsuccessful collision would not make any product, and a successful collision would take the two reactants, and you would have a new product. And similar thing over here. Here is emphasizing orientation. So notice that this first one says no reaction. So when your carbon monoxide and oxygen come together and they are not properly aligned, there will be no reaction. But if they are properly aligned, when they collide, there will be CO2 formed. Also, make sure you write down this definition for collision theory. Okay, so collision theory and equilibrium. Think about this. If you have a water bottle that is left open, and what happens over time to the water bottle with no lid? Compare it to a water bottle that's closed and maybe you leave it in your room for a really long time. What starts to happen to that water bottle? Well, if a water bottle's open, it will evaporate over time, and if a water bottle's closed, it won't. So, why doesn't the water in the closed water bottle evaporate or disappear? You might think that's obvious because it's closed, but something else is actually at play, which is called equilibrium. So let's watch a quick video about equilibrium. Then we'll return to that water bottle example and explain what's happening there. So there are check for understandings with this video.
In today's video, we're going to look at reversible reactions and see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right to indicate that the reactants can turn into the products. This means that it's a one-way reaction. Once the carbon dioxide is formed, it won't break back down into carbon and oxygen. In other reactions though, like this one here, we have a double arrow, which tells us that the reaction is reversible. The top arrow tells us that ammonium chloride can break down into ammonia and hydrogen chloride, which we call the forward reaction. While the bottom arrow tells us that the ammonia and hydrogen chloride can also combine to reform the ammonium chloride, which we call the backward reaction. So because both of these can happen, we call it a reversible reaction. Now, the important thing to understand is that the forward and backward reactions can take place at different rates. At the beginning of the reaction, there'll be loads of ammonium chloride, but no ammonia or hydrogen chloride. So the forward reaction will be really fast, but the backward reaction won't have started yet. As the reactants turn into products though, the forward reaction will slow down and the backward reaction will speed up. After a while, the rate will even out, and the forward and backward reactions will be going at exactly the same speed. At this point, the concentrations of the reactants and products won't change anymore, so we can say that the reaction is at equilibrium. So to clarify, at equilibrium, both reactions are still happening, but they effectively cancel each other out. So there's no overall change in the concentrations of the reactants or products. Of course, in reality, the molecules are still breaking down and reforming, but because they do so at the same rate, there's no overall change in the concentrations. Now, something to point out.
All right. So this video went over reversible reactions, which is when reactions can go forward and backwards. And when those reactions reach equilibrium, they essentially cancel each other out. So returning to our example of the water bottle open and closed, if we're looking at a water bottle that's open, the rate of evaporation or the rate of the water becoming water vapor is much faster than the water vapor is able to turn back into water. If the water bottle is closed, the evaporation of water turning into water vapor is happening at the same rate or speed that the water vapor turns back into water. Hence why the amount of liquid doesn't change over time. So, why does it happen with the closed water bottle? Well, that's because this is called a closed system. And that part's kind of obvious. because the water vapor can't escape. If there is no lid on the system, or if the system is not closed, we call that an open system. So you might think that if you're looking at a water bottle, the water is not doing anything. It's actually not true. The water is turning into water vapor, and the water vapor is turning back into water, but it's happening at the same rate that you can't even tell it's happening. The only evidence that you have is that there starts to be precipitation on the inside of the bottle. And the phenomenon when those rates are happening at the same time is called chemical equilibrium. So, chemical equilibrium is when the forward and reverse reactions happen at the same rate, meaning the rates are equal. Reactions are reversible in chemical equilibrium, which means they go in both directions, and they're annotated with an arrow with two directions. And the concentrations stay constant. They're not necessarily equal, but the concentrations or amounts stay the same because essentially they cancel each other out. So our example is water liquid turning into water vapor at the same rate that water vapor turns into water liquid. So again, water is becoming water vapor at the same rate that the water vapor becomes a liquid. And this does not mean the concentrations are equal. So this part is the part that always trips people up. What does it mean that the concentrations are not equal? Well, think about the video that we saw. It said that it's not necessarily that those people will be equal amounts. It just means that the amount of people in either category is no longer changing. Similar to if we had this water bottle here or beaker, we can argue that there's actually more water vapor in this beaker than there is water liquid. If you look at it, it's just a small amount of liquid. So the concentration or amount of water vapor is not equal to the amount of liquid water. But the concentrations or amounts are staying the same, but they're not necessarily equal. This concept was shown in the video with this graph, which I think is really helpful. So your forward reaction is the regular people turning into the discombobulated people, and your reverse reaction would be the discombobulated people turning back into the regular people. So this graph shows that the number of transfers, or the rate or speed at which this is happening, eventually comes to a point where they are the same. This is equilibrium. However, that doesn't mean that it's necessarily 50-50. This could be 500 discombobulated people, and this could be 200 regular people, but those numbers are going to stop changing because the rate of the reactions going in either direction are equal. And the effect is that they essentially cancel each other out. So even though the reaction is still happening, they cancel each other out and these numbers stay constant. So key point in equilibrium, concentrations stay constant and rates are equal. All right, so that's it for the lesson. One other thing that I want to point out is on your Google form, I divided up the Google form by questions that go with each video, and I reposted the video here just to make it easier for you to navigate. Okay, so head on over to your check for understandings, and I'll see you over at assignment 1 after this.